Hello everyone, welcome to Memoneat. I am Aprajita, your chemistry SME. I welcome you all. So I hope all of your preparation is going well. So we are going to have our PPT 6 on the next Sunday, right? So I hope all of you are doing well for the preparation. And today we are going to revise another chapter, that is chemical bonding and molecular structure. See, if you want to study this chapter in detail, we have already uploaded the video lectures for this chapter in our YouTube channel. In the chemistry playlist, you can go and watch the lecture of this chapter where I have completely covered this chapter in detail. Okay, so now today we will be doing the revision only. Okay, so we will be doing revision. Along with that, we will be solving some questions also to give you an idea about what kind of questions are asked in the NEET examination and how you can prepare for the a particular type of question. Okay, so this chemical bonding and molecular structure chapter is actually a very basic chapter also, but it is important as well because it carries good weightage in your exam. Okay, so we are going to start the revision of this chapter. So in the first case, if we talk about the chemical bonding, okay, so firstly we know that a chemical bond is a bond, you can say it is the creation of a chemical compound by forming a chemical link between two or more atoms, molecules or ions. Okay, means whenever two or more than two atoms, molecules and ions, they are combining together chemically, okay, there is a linkage between them, that is chemically we call it as a chemical bond. Okay, and those resulting molecules or whatever species are there, they are held together by the chemical bonds. So there are different types of chemical bonds that we study in chemistry, that is the ionic bonds, covalent bonds, hydrogen bonds, polar bonds, then there are coordinate bonds as well. Means there is different kind of bonding. So this is, I told you now, this is a basic chapter. So if we want to study about the basics of chemistry, we need to know about the chemical bonding, how the chemical bonding takes place and how the things happen. Okay, now the thing is that there are two ways of forming a chemical bond. All right, firstly, either an atom can lose or gain an electron, means loss or gain of electrons can happen. All right, or an atom can share the electrons. Okay, means sharing of electrons can happen and loss and gain of electrons can happen, which will result in chemical bonding. Okay, and based on that we have different types of bond. Let's do a quick revision based on that. So first one is the ionic bond, students. So ionic bond is that chemical bond which is formed when electrons are transferred from one atom to another. Okay, means there is no sharing, there will be loss and gain of electrons. Okay, so whenever there is transfer of electrons from one atom or molecule to another, means one atom loses the electron in this process and that particular electron will be gained by another atom. Okay, and when this electron transfer happens, one of the atom gains a negative charge, which is referred to as anion, and the one that carries a positive charge is referred to as the cation. Okay, and so this cation and anion that is formed, so these are held together by electrostatic forces of attraction. Okay, because obviously opposite charges attract each other, so they will be held together by electrostatic forces of attraction, which are strong forces. Okay, means, and the difference in charge, so if there is higher difference in charge between the cation and anion, stronger will be the ionic bonding. Okay, so how this ionic bond is formed, you know that atoms are electrically neutral, so they have equal number of protons and electrons. So if an atom loses an electron, number of protons will be more, an atom will gain a positive charge. For example, a very basic example, let me take, it's for sodium, right? Sodium loses an electron to form sodium ion. And why are they losing these electrons? To become stable, right? To acquire the noble gas configuration, right? No, noble gases which are already stable. So to acquire the noble gas configuration, the atoms loses or gains electron. Okay, So it will become positively charged. In the same way, if I talk about gain of electron like chlorine. So chlorine just require one electron to become stable. So it will gain an electron and it will become chloride anion. Now we will be calling it as an anion. So it has the nearest noble gas configuration like that of your argon. Okay. So in this case, the atom has become negatively charged. So when this electron, the electron that sodium loses, it is gained by chlorine. So these many sodium ions and chloride ions, they can combine to form a compound which is known as sodium chloride. Okay. And sodium chloride is an example of ionic compound. Alright students, so this is how your ionic bond will be formed. Alright. Okay, now next if I talk about the factors, now this is an important topic. See, I am discussing the important topics of this chapter from where the questions can be asked. Now you know ionization energy is the energy required to remove one electron, to remove the most loosely bound electron from the outermost shell of an isolated gaseous atom. Okay, that is known as ionization enthalpy. Means if I want to remove this electron from sodium, I need to supply certain amount of energy, that will be the ionization enthalpy, and then this electron will be removed. So what I want for ionic bond, I want that the ion should be formed easily, right? So the ion will be formed easily when the ionization energy is less. Means if I need to provide less energy, so in that case only the ion will be formed readily, no students. Okay. So that is why we say ki lower the ionization enthalpy and it will be favoring the formation of ionic bond. Okay. Now reverse happens when electron is gained by an atom. So means the enthalpy change that occurs or the energy that is released when an extra electron is added to isolated gaseous atom, it will be known as the electron gain enthalpy or electron affinity. Okay. So for example, when chlorine it actually gains electron, see, it will be gaining an electron, okay, and it will be becoming chloride ion plus some amount of energy would be released, that will be known as electron affinity or electron gain enthalpy. So means if an atom has more tendency to accept an electron, more energy would be released. So it means higher the electron gain enthalpy, more readily the anion will be formed and it will be favoring the ionic bonding. It means lower ionization enthalpy and higher value of electron gain enthalpy favors ionic bond. You have to keep that in mind. Okay. Next, lattice enthalpy, you know that amount of energy released when 1 mole of crystal lattice. Crystal lattice means, so they are not forming any molecule. Okay. So crystal lattice are formed there where there will be lot of positive and negative ions which are combined together. Okay. So that's how crystal lattice is formed. So higher lattice energy means greater will be the stability or the strength of the ionic compound. Okay. So that was something related to the ionic compounds. You must know the properties of ionic compounds as well, like they have high melting and boiling point. So they are soluble in water in your molten or like aqueous state. Okay. And these are the points, good conductors of electricity also. So these points you have to keep in mind. So now let us talk about the next type of compound, students, or the next type of bonding, that is covalent bond. So you all know that covalent bond is the bond that is formed by the sharing of electron. Means whenever there is no loss or gain of electron, but the electrons are shared by both of the atoms or all the atoms that are present in the molecule, that is known as the covalent bond, right? Like that is formed between the hydrogen molecule, oxygen molecule, and nitrogen is there. So we have our organic compounds in which covalent bonding is there. Okay. So covalent bonds, you know, they can be polar and non-polar. Okay. So if the electrons are shared unequally, so that is called as a polar covalent bond. Let me give you an example. So for example, we have hydrogen and chlorine. HCl molecule is there. It is formed by the sharing of electrons between hydrogen and chlorine. Okay. Now what happens is, that chlorine is more electronegative than hydrogen, so it has more tendency to attract the shared pair of electron towards itself. So as a result, it will be carrying a partial negative charge and hydrogen carries a partial positive charge. So we will say that HCl is a polar covalent molecule, okay, because the electron pair is pulled more towards the chlorine and it is away from the hydrogen. Okay, another example is water. In the case of water also, students, you know, hot oxygen is more electronegative than hydrogen, so oxygen will pull electron towards itself, okay, and hydrogen say away. So that is how you can say ki there will be a polarity, means poles will be developed, partial negative and partial positive charges would be there. Now again, if we have your non-polar molecule, in that case, like I have example of hydrogen, oxygen, chlorine is there, means when two same atoms are there or atoms of similar electronegativity. So in that case, the shared pair of electron will be lying in the center only, means it will be shared equally between the atoms, and if it is shared equally between the atoms, we call it as a non-polar covalent molecule. So you must know about the polarity and the non-polarity as well. Okay. Next, students, if I talk about Lewis symbols, this is also an important concept of this chapter. So Lewis symbols, so these were given by Lewis, who was a scientist. So actually, he told us that whenever we are writing any atom, we don't have to write all the electrons that are present in the atom. So to make the representation easier, only the valence electrons are written, and that too they are written as a dot. Okay, means I just need to represent the valence electrons as dot. Okay. For example, if I have hydrogen, hydrogen has just one electron, so I'll be representing hydrogen with one dot. Okay. Then we have helium, so it has two dots, so I'll be putting two dots, so it represents two valence electrons. Let's say if I am talking about lithium, so how many dots I will put? Its configuration is 2, 1. So I'll be just putting one dot because there is one valence electron. Similarly for carbon, I will be putting 4 dots. But the thing is that these dots have to be symmetrical. Okay. So you must know how to write the Lewis symbols as well. For example, now if I talk about a methane molecule, so if I am asked to write the Lewis symbol for that, so I'll be first just putting 4 dots around carbon. Okay. Then I have to write hydrogens. Let's see how. So hydrogen with one dot, because each hydrogen has one electron, one valence electron. Now we will be putting circles where the octet needs to be complete. Okay. So in that case, what we will be doing? So for carbon, you will be putting a circle like this. Each electron is shared. And for hydrogens, like this. So these circles I am showing, but that's not necessary. So you can just write it like this as well. Okay. So here like this and like this. So here this is the Lewis symbol for your methane molecule. So in Lewis symbols, we are just putting the valence electrons. Okay, keep that in mind, not the other way. So we don't have to write all the electrons that are involved. Okay, only the valence electrons. So you know about the octet rule, right? Just now we have discussed about the bonding. So why this all bonding happens? Because atoms have a tendency to achieve 8 electrons in their outermost shell. Means they need to complete their octet. Of course, except for the hydrogen, it will complete the duplet because it has just one electron in the K shell. Okay. So for completing the octet, the atoms can lose, gain or share electrons. That is how chemical bonding happens. Okay, to complete their octet, they tend to lose, gain or share the electrons. Alright, just now I have given you the example for your methane. Okay, let's take an example of another molecule. Let's say I'm having water molecule only. Okay, now oxygen has how many electrons? Oxygen has 6 electrons. Okay, so I'll be putting 6 electrons. It needs 2 more electrons for completing the octet, means so it will be combining with 2 hydrogen atoms and it will be sharing 1 electron with each of the hydrogen. Now see, this oxygen has total 8 electrons, which is the octet is complete, and for hydrogen 2 electrons. So for hydrogen we call it as a duplet. Okay, so this was the octet rule that was developed earlier, and uh, to understand the chemical bonding ki why the atoms are losing, gaining or sharing the electrons. Okay, so we must have an idea about the octet rule as well. Okay, but there were certain limitations of the octet rule also. Octet rule could not explain all the type of chemical bonds and everything. Let's see what are the limitations of the octet rule. Okay, so students, these are the exceptions of the octet rule. Okay, the first one you can see here is the electron deficient molecules. So you can see that some molecules exist in which the atoms don't have a complete octet, but still those molecule exist, means the ones that are having less than 8 electrons. For example, beryllium chloride. Now beryllium is 2,2, right? And now it has shared 2 electrons with chlorine, so still it is having only 4 electrons in the outermost shell rather than 8, but still this molecule exists. Okay, so we have AlCl3, BF3, boron trichloride. These also molecules are having 6 electrons in their outermost shell. You can see 3 are already there for aluminium, 3 it has shared with chlorine. Okay, so how many total are there? 6 electrons. But again, so these molecules are known as electron deficient molecules because the octet is not complete. Okay, now the second point is the odd electron molecules. So in molecules which are having odd number of electrons like nitric oxide, NO, and nitrogen dioxide, the octet rule is not satisfied for all the atoms. Okay, one atom can have an octet complete, but all the atoms are not having a complete octet. Okay, like for here you can see 1 2 3 4 5 6 7. Nitrogen is having only 7 electrons here in this particular case. So the octet, again, it is not satisfied for all the atoms. Next is electron efficient molecules. Now there were electron deficient molecules also. There are some molecules that are existing which are having more than 8 electrons in their outermost shell. Okay, like phosphorus pentachloride. Now this phosphorus pentachloride, phosphorus already has 5 electrons in the outermost shell, plus 5 it has shared with chlorine. Now how many electrons it is having? Total 10. 10 electrons in the outermost shell. So this octet rule cannot explain these molecules as well. Similarly, SF6. Okay, SF6 is having 12 electrons in the outermost, like in the outermost shell of sulfur. There are 12 electrons. So again, it could not be explained, right? Now, there is like some noble gases, you know, noble gases already have an octet, right? Their octet is complete. They are having 8 electrons in the outermost shell, but still they combine with molecules like oxygen and fluorine to form number of compounds. Like xenon actually forms a lot of compounds with oxygen and fluorine. Krypton also forms it. So that's another limitation, right? We cannot explain how the compounds are formed despite having an octet complete, and it cannot explain the shape of the molecule plus the relative stability and energy of the molecules. We cannot get to know from the octet rule. Okay, now one more important topic I want to revise with you all is the dipole moment, because a lot of questions I have seen in the PYQs, a lot of questions have been asked from the dipole moment topic. Okay, now, what is dipole moment? You know that for polar molecules, okay, they are also called dipole molecules. Means they are having two ends, no, positive and negative. So these molecules, they possess dipole moment. Okay, and what is dipole moment? It is defined as the product of magnitude of charge. So the magnitude of positive and negative charge multiplied by the distance between the positive and the negative charge, that is known as the dipole moment, and it is measured in dBi units. Okay, so dBi is the unit for the dipole moment. For example, I am having a molecule of HF. Okay, so obviously fluorine will be having a partial negative charge because it's more electronegative, and hydrogen has partial positive charge. So how do we represent a dipole moment? By an arrow and the line. So the arrow, the head of the arrow will point towards the direction of the electrons, okay, where the electrons are more. So here it will be pointing towards the negative end. So that's how we represent a dipole. So these are diatomic molecules, but for polyatomic molecules, let's say I'm having a water molecule, okay. So it has a bend shape with 104 degree angle. Now you know, let me show it with some other color. that the dipole will be like this, okay, will be pointing towards the hydrogen, okay, like sorry, oxygen, because oxygen is more electronegative than hydrogen, but the resultant dipole will be the resultant of these two dipole moments, and it will be pointing like this. Okay, so here this will be the dipole. In this direction it will be the resultant dipole. So you must know about the resultant dipole thing as well. Okay, now it's not necessary ki wherever there is polarity there will be a dipole moment. For example, I have BeF2 molecule. Okay, obviously there will be polarity because fluorine is more electronegative, so dipole will be pointing towards this. But what can you see here is that the resultant dipole moment, okay, it is going to be 0. Now why it is 0, students? Because in this particular case the two dipoles are cancelling each other. Okay, they are cancelling each other, so the resultant dipole moment is 0. Same goes with if I take a BCl3 molecule. Okay, it's a planar molecule with a bond angle of 120 degrees, but again here the dipole moment are like towards the chlorine, but still here the resultant dipole is 0. Resultant dipole moment is 0. Why it is 0? Because again these dipole moment cancel the effect of each other because they are in different directions. Okay, so resultant dipole moment for BCl3 becomes 0. So if anybody asks you that is BCl3 a polar molecule, no, it is not a polar molecule because the resultant dipole moment is 0 in this particular case. Okay, so you must know about the polarity. So whenever they will be asking you about dipoles and polarity, so you must know ki which molecule is polar and which is non-polar according to the resultant, according to their resultant dipole moment. Okay, so these some examples I have taken in this case. Now I'll be showing you some questions that have been asked from this particular topic. So students, this is the question which has been asked recently in your NEET 2024 examination. It says identify the correct answer. Dipole moment of NF3 is greater than that of NH3. Three canonical forms can be drawn for carbonate ion. Three resonance structures can be drawn for ozone, and BF3 has a non-zero dipole moment. Okay, now the two statements are related to dipole moment, however two are not, but still see dipole moment carries a lot of weightage. Okay, now the first statement, you will read the first statement and I know most of us would readily say ki yes, this is the right answer if we have not studied this concept. So you know that NF3, if I talk about NF3 molecule like this, so a lone pair of electron is there, all right, and for NH3 also, so lone pair of electron are there. Okay, now all of us know कि fluorine is far more electronegative than hydrogen. So obviously the dipole moment of NF3 will be greater than that of NH3, right? So most of us would say कि yeah, first option is the correct option. But students, if I look at the direction of the dipole moment, so here it is in this direction for the fluorine. Okay, directed towards fluorine, and for lone pair it is directed towards the lone pair. So now you see that obviously there will be a dipole moment for nitrogen and fluorine bonds, okay, because fluorine is more electronegative. But don't you think that the net dipole moment will be a difference of these dipole moments, right? Obviously we have to subtract them now because they are in opposite direction. But in the case of ammonia, for hydrogen and nitrogen bond, the dipole is pointed towards nitrogen because nitrogen is more electronegative than hydrogen. And for the lone pair also, now they are in same direction. So here the net dipole moment will be the result of addition of all the dipole moments. Okay, so that is why the dipole moment of ammonia will be greater than that of NF3. This is a separate case. Okay, this has been discussed in your NCERT books also. That's why I say reading NCERT is very important. So this particular case has been specially discussed, and that's why they have asked in the NEET exam also. So that's why I have written here ki it's direct from the NCERT lines. Okay, so it means the first statement is wrong. Dipole moment of NF3 is not greater than that of NH3. Three canonical forms can be drawn for carbonate. Yes, for carbonate what happens is there are three oxygen, okay. So there is a double bond between one of the carbon and oxygen, okay, and 4 electrons will be there, and here I'll be having 6 electrons with a negative charge on these two oxygen. So in the same way, I can rotate this double bond between any one carbon and oxygen. Okay, in this case, here I'll be having 4 electrons, and here I'll be having 1, 2, 6 electrons with a negative charge, and yeah, यहाँ पर भी we will be having 6 electrons. In the same way, one more will be there. I can draw this as well between this carbon and this oxygen. Okay, so the other two oxygen will be carrying a negative charge, 5, 6, right, 6 electrons, and here 4. So can you see there are 3 resonance structures? So you know about the resonance structures now. Canonical, we can call them as canonical form also. So actually this is the right statement. Then 3 resonance structures can be drawn for ozone. Actually for ozone there are 2 canonical forms only. Okay, ozone is O3. So there is a double bond between one of the oxygen. Okay, and then it can be like this. So this is wrong. There are no 3 resonance, but there are only 2. BF3 has non-zero dipole moment. Now here also you can get confused because BF3 is a planar molecule like this. Okay. And obviously dipole moment will be there because fluorine is more electronegative. But you see for this bond, the resultant will be in this direction and they will be cancelling each other, these two resultant, and they will have a zero dipole moment. Just now I have explained you, right? So in this case, it will be having a zero dipole moment. So this is also wrong. So in this case, the answer is going to be option B. So see, it was a multi-concept question that knowledge of resonance as well as the dipole moment was required to solve this particular question. So yes, sometimes such questions can be asked in the exam where you require multiple concept knowledge to solve the question. So that's why we don't have to leave any concept, and it's very important to read the NCERT because mostly questions are asked from NCERT. Maybe it can be direct or it can be concept based also. Okay. So students, the next important topic is the valence shell electron pair repulsion theory, okay, which is known as the VSEPR theory as well. So it is again an important topic because again some questions can be asked. So this theory actually was used to predict the shape of the molecules. This theory talks about the shape of the molecule. Although there is no theoretical evidence behind this, but still we study this theory because it was given to describe the shapes of different molecules. Okay, so it was given by Nylander and Gillespie. So this theory actually says, I have taken the main points only. So the postulates are that shape of the molecule depends on the total number of lone pair and bond pair of central atom, which we call as the valence shell electron pair. Okay, means how many electron pairs are present in the valence shell of the atom. They can be lone pair also, they can be bond pair also. So the shape of molecule will depend on those valence shell electron pairs. Now you know lone pair are the one which are not involved in bonding. Okay, means the ones that are not involved in chemical bond formation, they are known as lone pair of electrons, whereas bond pairs are the ones which are involved in the chemical bond formation. All right. Now how the shape is being described, so they this theory says that these electron pairs they tend to occupy such positions that there should be minimum repulsion between the electron pair, because you know whenever there is minimum repulsion it leads to maximum stability of the molecule. Okay, minimum repulsion means maximum stability. So these electron pairs they arrange in such a way that there will be minimum repulsion. Okay, and according to this valence shell electron pair repulsion theory, students, if I talk about the order of repulsion, so the lone pair repulsion is maximum, then there will be lone pair bond pair repulsion, and there will be bond pair repulsion, which is the least, because lone pair are concentrated on the atom only. Okay, if I'm like, let's say I'm having this ammonia molecule, so it has one lone pair and 3 bond pair. So bond pair though is shared between the two atoms now, so it's away from the central atom. But if I compare the bond pair and the lone pair, so lone pair will be concentrated more on the atom. So that is why lone pair repulsion would be the maximum, because they'll be much closer to each other. Then lone pair bond pair repulsion, at the end bond pair repulsion. Okay. So we need to consider both the bonding as well as the non-bonding electrons. Now see, these are the some shapes that have been given for the molecules. So if I have AB2 type molecule, so it generally has a linear shape. Okay, means the bond angle is 180 degree. For example, I can take BeCl2 molecule. Okay, so that's linear. Then there is trigonal planar for AB3 type molecules. Here I am not it's the general shapes. Okay, the general shapes are given. We are not talking about lone pair bond pairs as of now, like BCl3, BF3. So these are planar, trigonal planar molecule, and the bond angle is 120 degree. All the bonds lie in the same plane. Then there is tetrahedral shape. For example, methane. AB4 type molecule if you have, okay, means four different atoms are combined with the central atom. So that's methane. Like methane, it has a tetrahedral shape. Okay, where the four bonds are pointing towards a tetrahedron having bond angle of 109.5 degrees. Okay, then trigonal bipyramidal shape means in trigonal bipyramidal shape, three bonds are in a plane which are known as equatorial bonds, and the two are perpendicular to them, means at 90 degree. So they are known as axial bonds. Okay, so for example, we have PCl5, phosphorus pentachloride. AB5 molecule clay, we have trigonal bipyramidal shape. Okay. Then octahedral shape is there, students, in which I have AB6 type molecule. Four bonds are in the plane like this, and two are at 90 degree, means above the plane, and one is below the plane. For example, SF6 molecule. So these are the shapes of the molecules that are given according to the valence shell electron pair repulsion theory. But here I am considering normal molecules ki all the bond pairs are there, but what if the lone pairs are there? So because of these repulsions, the shape of the molecules are going to change. So how they are going to change? Let us see that. So as you can see here, students, this table tells us about the different geometries. Now this one I have already told you, EX2 type means AB2 type molecule having linear shape. Now in trigonal planar, let's say instead of two like three bonds, if there is one lone pair. Okay, so because lone pair bond pair repulsion is more than the bond pair repulsion, so the bond angle becomes less than 120 degrees. Because of the lone pair bond pair repulsion, this angle becomes more. So the shape, instead of trigonal planar, it becomes a bend shaped molecule. For example, for SO2 we have sulfur dioxide. Okay, in the same way, if there is AB4 type molecule, then it's tetrahedral, but again if there is one lone pair, so it becomes trigonal pyramidal. Okay, and the bond angle becomes less than 109 degrees. What happens in your ammonia molecule? Okay, so again because of the lone pair bond pair repulsions it has. Now if there are two lone pairs, it can happen out of four, two lone pair can be there. For example, the very good example for this molecule is your H2O molecule, which has two lone pair on oxygen. So again the bond angle will be much less than 109 degree, and it will be having a bend shape instead of tetrahedral shape. Same goes with AB5 trigonal bipyramidal. So here again if one lone pair is there, so lone pairs, if they are there, they will be occupying the equatorial position, because here it will be minimum repulsion and maximum stability. You can see all the lone pairs are at the equatorial position, not the axial position. So the shapes will change from triangle bipyramidal to seesaw shape, then T-shaped molecule, and linear molecule if there are three lone pairs. Okay, same goes with octahedral. Again here, but now in this particular case, the lone pair are occupying the axial positions. Okay, so here square pyramidal, square planar, and T-shaped molecule will be formed. So from this table you can get to know ki what type of geometry a particular molecule will be having. So if you are given a particular molecule, you need to find out how many lone pair and how many bond pair of electrons it is having. Okay, so from that you can predict the shape of the molecule by knowing the number of lone pair and bond pair of the electrons. Okay, so that's how this VSEPR theory or valence shell electron pair repulsion theory was used to predict the shape of the molecule. See, there was no theoretical explanation ki why this is trigonal pyramidal only or why it is bent only, but these shapes were just predicted on the basis of minimum repulsion between the electron pairs. Okay. So students, the next concept is hybridization. Before we study the concept of valence bond theory, so we can revise hybridization. So you know, hybridization is the mixing of atomic orbitals which are of the same atom but they have slightly different energies. So they redistribute their energy and new orbitals are formed which have identical energy and shape. Okay, so for hybridization, we all know that only orbitals which have comparable energies and belonging to the same atom can be hybridized. Means 2s and 2p orbitals can hybridize with each other. 2s cannot hybridize with 3p or 3s cannot hybridize with 2p. Okay, sometimes. So that is what can happen. Then the number of hybrid orbitals created equals the number of total orbitals combined. Means if I am having one s orbital combining with the 3p orbitals, okay, the total orbitals will be formed will be 4. Like in sp3 there will be 4 orbitals formed. Okay, so hybridization does not require participation of all half-filled orbitals. It's not necessary. Okay, even the orbitals that are totally filled but have slightly varying energies can participate in hybridization. Okay, then hybridization does not happen in isolated atom. Okay, so isolation mein jab atom pada hai, then hybridization will not happen. It will only happen when the bonds are being formed. Okay, and the type of hybridization also tells about the molecule's geometry. Okay, see, now Vesper's theory could not explain why the molecule is having a particular geometry, but when we study this valence bond theory, when we study the concept of hybridization, we get to know that the hybridization of the molecule will tell us about the molecule's geometry. Okay, and to determine the shape of the molecule as well. And the hybrid orbital is larger lobe is always positive, like we have two lobes and the small lobes will be negative. So let me show you a flowchart. So we have discussed in detail in our lectures. So there are different types of hybridization. Okay, so in that case, if I am having one s and one p orbital combining, so we get an sp hybridization like in BeF2. So hybridization will be sp hybridization. If one s and two p orbital are combining, we get sp2 hybridization. Okay, students. And then if I am having 1s and 3p orbitals combining, that is sp3 hybridization. Then d orbitals can also combine. Okay, some atoms like phosphorus is having empty d orbitals, so electron can jump onto the empty d orbitals also, and in that case d orbital can also participate in the hybridization. So the hybridization will be sp3d. Now if again two d orbitals are involved, so sp3d2 hybridization can also be there. And you know, in some complexes inner d orbitals can also participate, like we can have dsp3 or d2sp3 hybridization as well. Okay, but these are the important type. Now you see, if sp hybridization is there, then the shape of the molecule would be linear. From the hybridization we can get to know the shape what we were discussing earlier. No, for sp2 hybridization it's planar. For sp3 again tetrahedral shape. For sp3d trigonal bipyramidal shape, and for sp3d2 octahedral shape. So here we can explain that why the shape of the molecule is like that only, which we cannot explain in the Vesper theory. Okay, so the shape of the molecule or the geometry of the molecule can be determined by the hybridization. Okay. So students, now that we have understood the concept of shape of the molecules, I have one question for you which is also a PYQ. Let us solve that. So here we have to match the list 1 with list 2. There are 4 molecules given to us, okay, and we need to find out the shape of the molecule. So we can do it using the valence shell electron pair repulsion theory. Now I have ammonia. Okay, so for ammonia you know the shape, but let me tell you, so it has total 5 electrons in the valence shell. Okay, and out of 5 electrons, so 3 electrons are involved in the bonding with 3 hydrogen atoms, means there are 3 bond pairs. Okay, and there will be one lone pair of electrons because 2 electrons are not involved in any bonding. All right, So in this case, I have this AB4 type molecule. So it would have a tetrahedral shape, but it is not tetrahedral because there is one lone pair. Now we can go back to our table and we can find out the shape of the molecule. So here you can see that if there is one lone pair and three bond pairs are there, so the shape instead of tetrahedral it becomes trigonal pyramidal. So from here I can say that the shape of ammonia is trigonal pyramidal. For A it's 3. Alright, now I have ClF3 molecule. So how can I determine the shape of ClF3? Now you know that chlorine has total 7 electrons in the valence shell. Okay, and out of 7 electrons, 3 are involved in bonding, means there will be 2 lone pairs. Okay, 4 electrons will be left, na? 3, 7 minus 3, 4 electrons, so they will be lone pair. Means 2 lone pair of electrons and 3, abhi to I am just writing it like this only. Okay, so now it has become AB5 type molecule which is having 2 lone pair of electrons. So just look at AB5 type molecule having 2 lone pair of electrons. So it will be a T-shaped molecules because these 2 lone pair of electrons will be occupying the equatorial position and it will be a T-shaped molecule. Okay, like this. So I can draw it like this. 2 lone pair, one fluorine, and the other 2 fluorine will be occupying the axial position. So it is having a T shape. For PCl5, you already know, students, that for PCl5 there are 5 bond pairs. Okay, for phosphorus has 5 electrons and chlorine, 5 chlorines are attached. So it means it will be trigonal bipyramidal shape. Okay, and for BRF5, again out of bromine I have 7 electrons, so it means 5 are required in bonding, so only one lone pair will be there. Okay, so it's a AB5 type molecule which is having one lone pair. Obviously here though I'm just left with one option that is correct, but if you don't know, so just have a look. AB5 type molecule. Okay, so it's BRF5, no, with one lone pair. So sawhorse or okay, square pyramid it is written. Just let me see, it's BRF5 or BRF6. Okay, so there are 5 bond pair. Just a minute. 5 bond pair are there now with one lone pair. So AB6 type molecule hua, which is having one bond pair. So let's see the shape of the molecule. You can see here that AB6 type molecule with one bond pair, so one lone pair. So lone pair will occupy the axial position. So it will be having a square pyramid shape. So I can draw it like this: bromine. So 5 fluorine will be there. See, the position of lone pair is also important. Okay, and the lone pair will be occupying this position. So square pyramid shape. So this is how, by looking at the number of lone pair and bond pair of electrons, you can try to find out the shape of the molecule. Okay, now let's talk about the valence bond theory. So it tells us about the overlapping concept. Okay, overlapping of the atomic orbitals, and in this we have two types of covalent bonds, that is sigma and pi bond. So sigma bond is formed by the head-on overlap of atomic orbital, and this head-on overlap, it is along the internuclear axis. Okay students, so if there is a head-on overlap between the orbitals, it's called the sigma bonding, and there is direct overlapping, so that's why sigma bonds are the strongest covalent bonds. All right, so you know generally जो single bonds होते हैं, the single covalent bonds are your sigma bonds only. Like if there are different types of overlapping, we have SS overlap. So SS overlap like takes place in hydrogen molecules, so both the s orbitals 1s 1s are involved. Okay, sp overlap like takes place in ammonia, so the p orbitals of ammonia, sorry, nitrogen, they will like overlap with the s orbital of the hydrogen, so that's sp overlap. Now pp overlap, like in chlorine molecule, you can say कि the 3p orbitals of chlorine, they will overlap with each other to share one electron and they will form a sigma bond. Okay, so this is how a sigma bond is formed. Now pi bond is formed by the sidewise. Okay, sigma bond is formed by head-on overlap. Pi bond is formed by the sidewise overlap, but it will be perpendicular to internuclear axis. So that was along the internuclear axis. Here it will be perpendicular like this. So sidewise overlapping will happen. Okay, and you will get pi bonding. And in sidewise overlap, the overlap is substantially small. Okay, there is a small degree of overlapping, so that is why pi bonds are weaker than the sigma bonds. So pi bonding will be happening between the pp orbital. Here you can see the p pi bonding is given here. So if we talk about double and triple bond, so double bond may let's say carbon carbon double bond is there, so it's 1 sigma and 1 pi bond, whereas in triple bond there is 1 sigma and 2 pi bond. So that you must know. Okay, so that is the main concept related to the valence bond theory. The next theory is the molecular orbital theory. So students, the molecular orbital theory, it is related to the concept of overlapping of atomic orbitals. Okay, so it says that the overlap orbitals of the connected atoms, they lose their distinct character and they overlap to form bigger orbitals. So this theory talks about the molecular orbitals, means when atoms are going to be joined together, they will combine, the orbitals will combine, they will overlap to form molecular orbitals. So molecule, just like atoms have atomic orbitals, molecules have molecular orbital, which are similar to the atomic orbital only. Okay, the difference is that in the atomic orbital there is only one nucleus, so we'll call that as monocentric. But in molecular orbitals, the electrons move under the influence of various nuclei, which we call as polycentric. Okay, so the features are that molecular orbitals exist around the nuclei of molecule, just as atomic orbital exists around the nucleus of atom. Okay, molecular, now whenever the molecular orbitals are same, now their identity changes. Now they are not same as the atomic orbitals from which they are created. Okay, and in the molecular orbital, the constituent atoms valence electrons, they are thought to be moving under the effect of all the nuclei of participating atom, not just one nuclei, all the nuclei are there. Okay, again molecular orbitals also have varying energy levels, they have different energy levels. Okay, and the shape of the molecular orbital is determined by the forms of atomic orbital they are created from. And again molecular orbitals are also filled in ascending order of energy. Okay, and the Aufbau's principle, Hund's rule, Pauli's exclusion principle that we have learned in the last chapter, no, they are the ones only that govern the filling of electrons in molecular orbitals also. In atomic orbitals we use these three rules now. So these three rules are used in the filling of molecular orbitals also. So let me show you the orbital diagram. So it is for the homonuclear diatomic molecule, except oxygen, fluorine and neon. So oxygen, fluorine or neon may there is some difference, okay, that I will tell you. But otherwise for other homonuclear diatomic molecules we have this order. So you can remember this order. So say 1s and 1s will combine. So there are two type of orbitals formed. One is the bonding orbital, which is lower in energy, and the other one is the anti-bonding orbital, which is higher in energy. Okay, so bonding orbital will be represented like this, sigma 1s, and anti-bonding will be represented like sigma star 1s. So we have sigma 1s, then we have sigma star 1s. Okay, after that 2s orbitals come. So again sigma 2s is there, then sigma star anti-bonding, okay, means 2s is there. After that we have p orbitals. Now p orbitals are involved in pi bonding also. Okay, so okay, here now it's written wrongly, it's not star. All right, so firstly we will be having the pi orbitals, they will be having lower energy. So pi 2px and pi 2py, they have equal energy. Okay, then we have sigma 2pz. So 2pz will form sigma bond. Now we will be having the anti-bonding, means pi star 2px and pi star 2py, means the anti-bonding, and at the end we will be having sigma anti-bonding 2pz orbital. And in the same way, if we are talking about like hydrogen molecule, let's say, so in hydrogen molecule there will be two electrons only, like one in here and one here. So in that case for hydrogen the orbital diagram will be just this much, like sigma 1s 2. both the electrons will be filled in the bonding orbital only. So for hydrogen it will be sigma 1s2. Okay, so that's like this order you must remember, then you can fill it for any given molecule. Now from this molecular orbital diagram, a lot of questions are being asked. So the questions are asked on the bond order and the magnetic behavior of the molecule also. Like if I ask you the bond order of hydrogen molecule, so how will you calculate the bond order? So let me show you. The bond order is equal to the number of electrons in the bonding molecular orbital minus the number of electrons in anti-bonding molecular orbital divided by 2. So for hydrogen, the configuration is sigma 1s2, right? So it means 2 electrons are in the bonding orbital, no electron in anti-bonding. 2 minus 0 upon 2, so 1. The bond order means there is only one covalent bond between the hydrogen atoms. So this is how we will find out the bond order. Okay. Now magnetic and non-magnetic character. So you know about this. So if all the electrons are paired, so we will be calling it as a diamagnetic molecule. For example, hydrogen. Hydrogen may we have paired electrons now, so both electrons are paired, so it's a diamagnetic. But if any unpaired electron is present, so that molecule will be paramagnetic. So again that you will get to know from your this thing, the molecular orbital diagram. And greater than number of unpaired electron, greater will be the paramagnetic nature, because magnetic moment is given by square root of n into n plus 2, where n is the number of unpaired electrons. Okay. Now this was the like energy order that I told you for other molecules, right? Sigma 2pz will come after pi 2px and pi 2py. But for oxygen, fluorine and neon, the sigma 2pz comes before the pi 2px and 2py. So this is the only difference that we are having in this particular case. Okay, so that you have to remember ki in these three cases the sigma 2pz will come first. Okay. So the only thing you have to remember is these orders, then you can fill the electrons easily. Okay, like for hydrogen I have to fill 2 electrons, I can fill that. For like helium, let's say for helium molecule He2, okay, so this question can also be asked. Now there are 4 electrons, so the for helium the configuration will be sigma 1s2 and the other 2 electrons will go to the anti-bonding 1s2 sigma star. Now if I find the bond order, so bond order for helium will be 2 minus 2 upon 2, so that will be 0. Bond order 0 means helium 2 does not exist, because it's a noble gas, this molecule does not exist, so here the bond order is 0. Okay, so in the same way such questions can be asked ki which type of molecule exists, then which is paramagnetic. They'll give you 4 options, they'll ask you which one is paramagnetic or which one is diamagnetic. Okay, so one such question I have, which was asked in NEET 2023, that we have to tell the correct order of the nitrogen molecule. Now for nitrogen the same order will be there, the one that I have told you ki pi 2px orbitals will be having lesser energy than sigma 2pz. Okay, so that will be the order. So let me show you for nitrogen. Okay, yeah, now you see nitrogen may how many electrons will be there? 7 plus 7, 14 electrons would be there, right? So sigma 1s2, sigma star 1s2. Okay, then it will be sigma 2s2, sigma star 2s2. Okay, how many electrons we have filled? 8. Now it will be pi. Okay, pi 2px2 pi 2py2. All right, how many are filled? 12 electrons, then sigma 2pz2. So this will be the correct order for the nitrogen molecule. Okay, so this is just you have to remember that 2pz will come after pi 2px and pi 2py. So the answer is going to be option number D. Okay, this will be the correct order. So this is how we are going to solve the questions for the molecular orbital theory. Just remember these two diagrams. Okay, so students, with that I have completed the important topics of chemical bonding and molecular structure. In case you are having any more doubts, you can let me know in the comment section and I'll try to solve all your doubts. So this is an important chapter, try to focus on it and do it religiously. Okay, if there are any doubts, try to solve all the PYQs, and as I always say, the NCERT line by line questions on your MemoNeet app, please do that as well. Okay, and prepare well for your BPT6. In case any doubts, please ask me in the comment box. All right, so we will meet in the next lecture. Until then, take care. Bye bye everyone.